Hello, so welcome back to another class. Today we will still be doing about vertical motion in a resisting medium. But if you remember last class, we have seen that we were doing vertical motion in a resisting medium, but when the particle was traveling downwards. So now what we will do, again we will do vertical motion in a resisting medium, but over here the particle is traveling upwards. I will try to explain this one by using this example which I've written on the board. Let a particle be projected vertically upwards with velocity u in a medium whose resistance varies as the velocity. If v be the terminal velocity, so that if x, v and t are the distance, velocity and time at any point, then all those things we have to find the greatest height as well as the time to reach the greatest height. So over here you see that we are mentioning the word terminal velocity again, even though it is for upwards motion, but we are still mentioning the word terminal velocity. So this is what we will do. Whenever we have to calculate terminal velocity, we will use downwards motion. Okay, so downwards motion will always be involved for the terminal velocity, even though it is for upward motion. Okay, so this is what we will do. So we have a particle, okay, it's projected with some velocity u. At any point of time, its velocity will be v. Okay, p can be anywhere on this part. Okay, and g, it is the greatest height that the particle attains. So at this, over here, the velocity it will be 0. That is the velocity at the greatest height. Okay, so what about the time? The time, we are measuring it from O, so the time over here will be 0. The time will be t, and over here it is denoted by capital T. T is the time to reach the greatest height. What about the distance? The distance over here, we are measuring it from O, so the distance over here at this point is 0. The distance at any point P, it is x, and the distance at the greatest height G, it is h. You can see here we have denoted it with h for the greatest height. Okay, so now we will solve. And over here, what are the forces, okay, that this particle will experience at each and every point? Okay, for example, the point P, the velocity is v. So if you see over here, the resistance varies as the velocity because it is traveling upwards. So the resistance will be downwards. It will be kV. It varies as the velocity at that point. Okay, and also the gravity is going downwards. Okay, g. Okay, over here I forgot to mention again resistance per unit mass. Okay, that is very important. Sometimes the resistance may not be given per unit mass. Okay, but for this question it is the resistance per unit mass. Okay, so now let us solve this question. Okay, because we will be dealing with both upward and downward motion, so I will write the equation separately. For upward motion, and over here we'll be writing for downward motion. Again, I repeat, I am requiring this downward motion just so I can find the terminal velocity. The equation of motion over here is m d2x dt squared equal mg minus mkv, because mg is acting downwards and mkv is acting upwards. Okay, whereas over here for upward motion, the equation of motion is d2x dt squared equal minus mg. Both of them they are acting upwards. Okay, so because we are calculating the terminal velocity, we will be doing the downward motion when v is terminal velocity. The acceleration will be 0, so 0 will be mg minus mkv, because this term over here is the acceleration and it will be equal to 0 when the particle has reached the terminal velocity. So again, I will be naming this equation as equation A. This will be required here. Okay, so sorry, it will be capital V. And over here, we can cancel M. G, we can replace it with KV. Okay, so G, we can replace it minus K, we can take it as common, V plus V. Okay, if you see the first equation that we want to find, okay, the first equation is dealing with velocity and time. Okay, so that's why I will be writing dv dt. Okay, instead of d2x dt square, I will be writing dv dt. Okay, so now we just separate the variables. Minus k dt. We will integrate. Now we put the limits. The limits, the particle is starting from the point O, so it will be u. It will reach the point P, so the velocity, it was small v. Over here, the time 0 up to t. Integrated. If we integrate, this one will be log v plus v, and over here will be minus kt. Over here the limits are from u to v. So next we will substitute the limits so that we can obtain this integral. Capital V plus u equal minus kt. Next, we will use properties of logarithms. Over here will be v plus v because it is the upper limit. V plus v over v plus u minus kt. So ultimately we will be having v plus v, v plus u equal e minus kt. And then, because we need the expression for the velocity, so small v, it will be v plus u e minus kt minus v. Okay, let me just check. Yes, that is the required expression that we want to find. And k, we can use g over capital V, gt by v. So we will be having this. This is equation 1. And if you remember the question, we also need to find the time to reach the greatest height. We can do it from this equation 1. Okay, we can do it from this equation 1 because equation 1 involves the velocity as well as the time. Okay, so in fact, what we can do from this equation over here, it will be much more simpler if we calculate the time to reach the greatest height from this equation. Okay, or if t is the time to reach the greatest height, okay, I will name this one as equation B. We can actually write this one to the side, doesn't matter. If t is the time to reach the greatest height, then over here instead of t, we will be replacing it with capital T. So kt. And over here log capital V, it is a constant, so we will leave it as it is. Similarly, the velocity of projection u, it is a constant, but what changes is this small v. At the greatest height, the velocity is 0. So that is why we will get that the time to reach the greatest height, it will be equal to minus log v upon v plus u. Okay, 1 by k. 1 by k minus 1 by k. Minus 1 by k. So if you don't want this minus sign, we can interchange the log. So 1 by k log v plus u upon v. And k, it can be expressed as g by v. So ultimately we will be having v by g log v plus u upon v. This one by using b. And this one by using a. So this is what we will get. Okay, so we have got 1, and also we have got the time to reach the greatest height, which is this. Okay, but why did I write this one to the side? Because I will still be needing this. This will still be needed for deriving equation 2. So from equation 2, for equation 2 we need a relation between x and t. So that's why we can write it as dx dt. Always remember that over here we can only interchange it into a derivative if the quantity is not a constant. Okay, for example, this capital V, it is a constant. So that is why we don't need derivatives for this. Similarly, u, it is a constant, so you won't be requiring derivatives. Okay, but this one, it can change because this one, it is p. It depends on the point p. So wherever, so when the point p changes its position, this velocity will also change. That is why I am using the derivative only for this small letter v. So this is what we will have. Next, we will separate variables. Next, we can separate the variables. Okay, dx dt. So dx. Okay. Actually, I will write it directly. V plus u e minus gt by capital V dt minus v dt. Okay, I'm writing it directly. This one is a constant. We can take it outside of the integral sign. Okay, similarly, this one we will have it like this. The integration is from O to P, so from O 0 to x. And over here, this is integration for the time 0 to t. 0 to t. So this is what we will be having. Now all that is left is integrating. So this one will give us x, v plus u. Integration of this one, it will be minus v over g e minus gt by capital V, limits from 0 to t, and for this one it will be minus v d. Okay, so this is what we will be having. Minus v by g, it is a constant. Okay, so now we just need to put the limits for this. Put in the limits for t over here, we will be having gt upon v minus e power 0 minus v d. X will be minus v upon g, v plus u, e power minus gt upon v minus 1 minus v d. So this is what we will be having. Okay, just let me check whether this is the required expression or not. Okay, so it is the required expression. You just have to multiply this one with 1. Okay, this one with this will have, okay, this one with 1 will be having v by g, v plus u, and multiply this one with, here we will be having v by g, v plus u, e minus gt upon v minus v d. So this is the required expression with this expression 2. Okay, so it's fairly simple. Right now we will require equation 3. Okay, for equation 3, For equation 3, we cannot proceed from over here because we have reached distance. Okay, we have reached this point x. Okay, and everything over here, okay, it's constant except the time and x. So we can no longer proceed from over here. So what we will do, again, we will rewrite the equation of motion. Again, equation of motion is d2x dt squared minus mg minus mkv. Okay, so this was the equation of motion that we had. Now, if you take a look at equation 3, it is a relation between small v and x. So instead of d2x dt squared, we will be using v dv dx. M will get cancelled. G, it is again equal to kv. So again, we will take common k. This is what we will be having. K dx. We will integrate 0 to x over here from the point u, from u up to small v. Okay, so this is very similar to what we had done when we were doing downwards motion. Okay, the only problem is when integrating. How will we integrate this one? Okay, we can, because over here we need plus v. Okay, plus v, it's already here, plus v, so we don't have to do anything. But we also need v plus v in the numerator, so what we will be doing is rewriting it like this. We will rewrite it in this way. Okay, but we also have to subtract minus v. So I have added capital V and I have subtracted minus v. I am doing this because I need this capital V plus v over here. So now we will split the integral. We'll be having v plus v minus capital V dv equal minus kx. Again, u to v. Over here we'll be having 1, so we'll be having dv minus, over here it is a constant, we can take it outside, u to v dv upon capital V plus v. So this is what we will be having. Now the integration is very simple. Over here integration of this one will be will be v, and integration of this one, it is log. So this is what we will be having. Now we just substitute the limits. This one is small v, v minus u minus capital V, and over here we will substitute the limits. V plus small v minus log v plus small u. Next, we will use the properties of logarithms. Capital V. So over here we will be having log v plus v divided by v plus u equal minus kx. Okay, just let me see how much we want to find. Okay, this is actually the required expression. Okay, we just have to substitute in the value for k. K, it is g by capital V. G by capital V x. Okay, but over here minus, I will multiply the whole thing by minus gx upon v. Okay, this one will be having minus v minus u plus v log v plus v plus u, and hence x will be v log v plus v upon v plus u plus u minus v. I have multiplied this minus over here, so that's why I'm having u minus v. This one is small v. Okay, so this is the required expression number 3. Okay, but if you see, there is still some more to the question. We still need to find the greatest height as well as the time to reach the greatest height. We had already found the time to reach the greatest height. So now the only thing that is left, we will have to find the greatest height. So at the greatest height h, so x will be equal to h and small v, it will be equal to 0. After using this, we can substitute it over here. So capital H, which is the greatest height, small v is 0 plus u. So this is the time to reach the greatest height. Okay, I think I made a mistake. Okay, it's g by v. Okay, it's g by v. Okay, g by v. Okay, v by g. And over here it should be v by g. Okay, so this is what we will be having. Over here we will be having v by g u. So this is the required time to reach the greatest height. So if I have to summarize what I have done, okay, we can either use dv dt, we can either use v dv dx, okay, as a summary. If I am using dv dt, this gives us a relation between velocity and time. If I am using v dv dx, I am getting a relation between v and x. This one will be used to find the capital T, the time to reach the greatest height. And if I am using v dv dx, this one will be used to find the greatest height. Okay, so that is a summary. If you have to find the time to reach the greatest height, it is best if you start with dv dt. And if you need the greatest height h, it is best if you start with v dv dx. Okay, things will get done sooner, okay, if you follow this technique. Okay, until next time.